techniques we use at RadiaSoft to help with our quest to develop maintainable software quickly and robustly. I'll give an overview of the problems we face, describe 4 techniques that help us write maintainable software quickly and robustly. And I'll give a couple of links at the end and answer any of your questions. First, it's best to define our problem. We are modernizing software developed for desktops and the command line, allowing anybody to use it via a web browser in a single-page application, so-called SPA. The framework and collection of codes it implements is called Repo. It's open source, and we're supporting 20 different codes. We would like users to have a seamless experience as they switch between codes, and Repo makes it easy to export input decks for many codes to re-import them. Repo allows users to share simulations via URLs, share compute resources, and to execute on supercomputers, all in the same browser-based UI. One of the features that's unique is that you can convert a simulation from one code to another, or create pipelines between codes. That's a new feature we're working on. The ultimate goal for the software team is to be able to rapidly develop a UI and backend for a code in a few weeks. Let's go through quickly some of the codes to get a flavor of the diversity that Repo has to handle. Repo is used to lay out and design thermionic converters with the Fortran particle in cell code work. These vacuum nanodevices convert heat to electricity. Repo Activate allows users to upload arbitrary data sets to classify them and perform regressions as well. Here's an example of classifying flowers by type based on sepal and petal conventions. Repo SRW is used to design synchrotron beamlines with a drag and drop interface. Repo Flash is a proprietary code of the University of Rochester. In order to run a Flash simulation, Repo has to compile the Fortran code on the fly. Users can upload Fortran files to be included in the simulation library. Repo Controls is a real-time Accelerator beam control app using ML to optimize beam position. Controls allows optimization via the particle accelerator simulation code, MATX, or by connecting a live accelerator control system. As you can see, there's quite a range of domains and features Repo has to support. And there are many differences between a web app like Repo and a scientific code like MATX. So this creates many issues for the software team. Customers need Repo to be adapted quickly when their code changes. While RadiaSoft has many scientists, the software engineers have no scientific training. By the way, please don't ask me what a capillary discharge plasma is. This creates an impedance mismatch, which we have resolved by treating codes abstractly. The software team is tasked with adding codes to Repo, often with very short timelines. On top of this, codes do not interoperate even when they are designed for the same problem space. The codes themselves are not usually set up with automated test suites, so many aren't very robust. Input deck formats change as well as algorithms, which tend to break simulation runs in strange ways. I'll now talk about a few techniques that helps Repo be stable in the face of these challenges. Code configuration files are also known as input decks, that's a leftover from the good old days of punch cards, often have many parameters, especially as a code gets older. Code output is complex, often requiring the use of custom APIs to read them. Repo uses a technique called declarative programming to describe the code without explicitly listing commands or steps that must be performed to implement them. The use here, it also overlaps with domain-specific languages, or DSLs, if you're familiar with them. For each code, Repo defines a schema, which specifies the inputs, outputs, UI layouts, and so on. A schema is a formal specification which is interpreted by the Repo UI and backend to validate input, present graphs, etc. I'll also show an example of that shortly. This is probably the most important technique we use for speeding up development. Sometimes we can parse the code itself to partially generate the schema. Other times we parse documentation. This greatly simplifies schema creation. The Schrepo UI downloads the schema to generate the input forms and present graphs and other output. The schema is used by the back end to route queries, validate input, to generate input decks, and generate graphs. When a new feature is required, it's often a simple matter of defining it in the schema. The UI and the back end then interpret the new feature automatically. Let's start with the native input decks. On the left is Synchrotron Radiation Workshop, or SRW, which models X-ray beamlines using wavefront propagation. On the right, Shadow, which models X-rays using ray tracing. The two codes should be interoperable, especially since their native input format is Python. However, they are not compatible. The example here is a compound refractive lens, which in SRW is a single optical element with a special CRL drift element. Shadow defines a 3-element CRL as 6 half lenses. There are many other differences. However, Schrepo is able to manage those differences via its standardized configuration format. By the way, the input deck on the right was generated by using Schrepo to convert from SRW to Shadow. Schrepo has a canonical format for inputs, which is shown here in JSON. This is the Beamline declaration for this particular simulation. The full JSON file is much larger. Standard formats allow the UI to interpret the inputs in a standard way. Without it, the UI would have to understand that Shadow has 6 elements for a CRL and SRW has 2. The backend is responsible for turning this canonical configuration into native input decks, which does involve non-declarative code. Standard form also makes it easy to translate between similar codes as we have here. In some cases, the specification is identical, as with the watch points in the bottom of each in this example. Finally, here's the schema, which should make it a bit more sense now that we know what it is describing. This is the CRL model for each code. Each version of a CRL has many attributes: title, position, focal plane, and so on, some of which are not shown. Each field of a model specifies the internal name followed by a list of values. For example, title is the name of the first field, and it has a label of element name, and it is of type string. The default title is CRL, which makes sense. In a beamline, there could be multiple CRLs, however, each with its own title, for example, CRL1, CRL2, etc. The label may contain a unit in square brackets, for example, position is in meters. There are many other parts to the schema, which we don't have time to go into here. They all work in the same basic way. Just describe an aspect of the code purely and declaratively. Schemas allow us to have a single page SPA instead of having 20 different apps. Scientific codes are extremely complex. Features are often given higher priority over robust input parsing or error handling. This means that Schrepo has to be prepared for the unexpected or the unknown and unknowns. Schrepo also interacts with third-party systems like the supercomputers at NERSC or beamlines with custom interfaces that may not be designed for programmatic control. To protect Schrepo and our customers' data from the unexpected, the software fails fast when expectations and reality disagree. Sometimes a failure is recoverable, at least to give a reasonable error message. Most times, we let failures stop execution of the current request or operation. In Python, this typically means letting exceptions trickle up to the highest level code, which can log the error with a stack trace and return a server error or something similar to the user. In JavaScript, extra work is required because often JavaScript and its many libraries fail silently. Many UI frameworks work this way, and it's very disheartening to stare at a blank screen with nary a console message. This is what happens without fails fast. If there is a bug, the software fails eventually without any information about the root cause. With fail fast, we have clear stack traces and informative error messages. This greatly simplifies debugging, especially on the production system where we can't stop everything and run the server in a debugger. Here's an implementation of part of the plotting software for Srepo Cloud MC, which wraps OpenMC, an open source neutron photon transport modeling code. The function SimFrame returns a single graph, possibly part of a sequence of graphs. The first arrow on the left is an early exit from the function. If there's no mesh, return an informative error to the user, the second arrow. The second try block catches an error in write data to VTK. Here the error is caught and checked for a particular English language description. This is typical for codes. The wrapper has to parse natural language because scientific code errors are often intended to be read by a human. Programmatically, it's a bit more work, but necessary to give the user a useful error message. The fourth arrow is a fail fast for unexpected errors. If the runtime error does not match the unexpected error, go directly to jail, do not collect $200, and let the outer scope return a generic error to the user. Many times, people will put a pass to ignore the exception or a print statement and continue on in vain. You'll never see this in Srepo code, and if you do, please let me know. The next helpful technique is introspective programming. Some code wrappers can import native formats and others can't. Some have special fixups before writing simulation spec to the database, and others don't. Each code wrapper in Srepo only defines what it can support. We use introspection to determine if those features exist in a particular code. Sometimes we can provide a reasonable default. Most times we fail fast when a feature is requested that's not implemented. This is the dispatcher for the SimFrame function 2 slides ago. There are 2 types of SimFrame dispatches: report specific or generic. Initially, the SimFrame function was the only way to generate frames. Now, Srepo supports a more modular approach with report-specific functions. Introspection allows a dispatcher to feature test for both kinds of functions, as you see on the line with the second arrow, which also allows backwards compatibility. The first arrow is the common pattern for finding a wrapper, which is also known as a template. The template is found by calling import module, which dynamically searches for the module in an ordered list of Python packages. We do this so we can deploy open source Srepo along with wrappers for proprietary codes. These 2 forms of introspection also allow Srepo to be future-proof and backwards compatible, which is the next technique I will cover. RadiaSoft is a consultancy, and new code wrappers are needed upon customer request, often in a very short time frame. Other times, we have a bit of breathing room, fortunately. In order to keep up, code wrappers need to be updated at varying speeds. We use feature tests to detect which code wrappers are using the latest APIs. Srepo also allows users to export a complete copy of the code's JSON configuration file. Years later, that JSON has to be importable back into Srepo. The scheme itself is not static, however. We have to add new features frequently. Srepo employs a fix-up mechanism which allows importing old JSON against the new schema. Another way we manage change is by wrapping third-party libraries, so development can continue in other parts of the system without disruption. First, I'll talk about fixups. Here are a few of the many fixups for SRW, which is one of the oldest code wrappers. Data.models is the deserialized JSON you saw in the declarative programming section. The first conditional fixes up the data due to a change in the definition of sample factor from being specific to a report to being generically applied to the simulation as a whole. The next conditional adds a method to the intensity report based on the source type, undulator, dipole, etc. Finally, facility is no longer used, so it is removed from the configuration. All the fixup work this way, and they are using a form of feature test, which is the subject of the next slide. Many scientific codes use MPI, Interprocess Communication Library, first released in the 1980s. Due to its long history, MPI has many different implementations and 2 different specifications. In the early days of Srepo, we used OpenMPI. Now we use MPitch. In order to manage this type of change, we wrap MPI in a module. This is a generic technique for future-proofing code. Wrap third-party interfaces to enable change. Another problem with MPI is that it may not be there, or if it is there, it may not be enabled. The try block handles all these cases with two feature sets. Is MPI importable? And is there a COM world, a communication object? If either fail, then the variable R will be the first rank and C will be none. This ensures the op is always executed whether MPI is running or not. And to hammer home the fail fast point, the function fails fast robustly whether MPI is available or not. There were many techniques covered here, which were put in a few broad categories. I talked about how Srepo uses schemas and canonical configuration to simplify our code and ease maintenance with changing third-party scientific codes. We use fail fast to make Srepo robust in the face of unexpected errors in output. Introspection lets Srepo support codes with vastly different feature sets. Feature testing helps us future-proof our code, and automatic configuration fixups help us maintain backwards compatibility while growing Srepo. This is why research software at RadiaSoft is easy peasy. Thanks to the RadiaSoft team for using and improving the ideas in this talk. Special thanks to Evan Carlin for greatly improving the content of this talk. You can learn more by visiting our Srepo repository, which has an extensive wiki and access to all the source code. We have documented many of these techniques in our design hints page in the PyKern wiki. Please feel free to email me. You can try out Srepo for free or learn more about RadiaSoft at radiasoft.net. Thank you for watching. I'll be happy to answer your questions.
Awesome. Thanks, Rob. I apologize if you guys heard my dog barking. I had forgotten to mute myself. We'll go ahead and do our question and answer session now. Please go ahead and submit any questions you have with that Q&A button. We're going to start off with regards to fail fast, how do you decide when it is possible and or safe to recover from an error and when it isn't? I think you're muted, Rob.
That's the magic of it. You could just hand me the mic. So that's always a hard problem. You have to figure out what you want to see. And usually, like in the example I provided, if I want to present an error to the user, you can wrap it in a return value and give it back to the user. But if it's something that the user can't read, then you pretty much always have to just fail fast. So default is fail fast. And when you understand the errors as they're happening, they will happen in real time, you fix the code to support better error handling.
Okay, thank you. Next question up in the queue is, what are your thoughts on quote unquote standard data formats for interchange, such as Parquet and Arrow?
I don't know Parquet or Arrow, so I can't answer that question. Standard interchange formats are hard. We've worked with other groups, and in general, it's hard to define things like some codes will be meters, some codes will be millimeters, some codes will be centimeters, and as pointed out, even codes that are quite close, they just do things very differently, and even the way they measure can be different. So from the center of the optical element or from the edge of the optical element. So it's a hard problem, which we chose not to solve.
Okay. All right, thank you. And our next question is, how did you settle on JSON for the model schema? Are there cases when you can't represent some information about a code in JSON?
Actually, we're running into that a little bit now in that we're trying to generate the entire UI in React. And we've converted many of the codes over to React, where it reads the schema and there is no application-specific code at all in the user interface. That presents certain problems with the way React works, and we are having to basically include some amount of JavaScript in the JSON or in another module that gets included dynamically. But most of the times, everything is describable.
Okay. Awesome. Well, that brings us to the end of our webinar time. So thank you again to Paul, to Rob, RadiaSoft CTO, and thank you to all of our attendees for joining us. And we will see you next month in our next webinar series. Bye, everybody.